What's up guys, it's Simon Fiaz and today's video is on AQA AS level chemistry May 2019 paper 2. So question 1, state what was observed in each case, 6 marks and that's it. That's all that is for question 1. So I've got compound A, compound B and compound C. I want a region or combination of regions to distinguish between these two, compound A and B. Well, A is what and B is what? Well, B is a carboxylic acid, so I can just use sodium carbonate or hydrogen carbonate. So yeah, sodium carbonate, any named carbonate, right? Really, carbonate. And observation with A, no visible change, and with B, because it's a carboxylic acid, effervescence. Effervescence. Now, distinguishing compounds A and compound C. Well, the thing is, compound A is compound A and compound C. Well, compound A, sorry, is a ketone. So we can use Tollens region. Tollens region. And the observation with A, no visible change. Observation with C, silver mirror. Silver mirror. Outline the mechanism for reaction, bromoethane reacts potassium cyanide to form compound D. So methane, ethane, propane. No, sorry. Bromoethane. 3 CH2 Br. One pair of electrons, CH1N negative, carbon partially positive, Br partially negative, and then you form your CH2CN. Outline, give that UPAC name of D. Propane nitrile. Propane nitrile. Calculate percentage atomic economy for formation of D. Percentage atomic economy, M of desired products of M or reactants times by 100. In this case, I don't need to worry about moles. M of desired product formation of D. So it's going to be the M of that over the M of all reactants times by 100. So let's just check this first thing. CH3, CH2, Br, 1 per electron, CH1N negative charge. Attached carbon, CBr bond breaks. Perfect. Propane nitrile. And then the thingy, so then 12 plus 3 plus 12 plus 2 plus the MR of CN, 55, over the MR of this plus the MR of that, 174, times by 100, 31.6%. Question 3. Use the data to calculate final temperature of the water in this experiment. So, I'm going to use Q equals MC delta T. Q equals MC delta T. Therefore, delta T equals Q over MC. But the thing is, I can't find Q without I can't find Q because I'm trying to find out delta T. So I'm going to use delta H equals Q over moles. It's another equation you have to memorize. And therefore Q equals delta H times by number of moles. So therefore Q equals delta H, which is 1216. I don't care about negative, that just tells me it's exothermic. Temperature increases 1216 times by number of moles. Well, the moles of what? The moles of cyclohexane. So it's going to be the mass, so it's the difference between these two, 192.730 minus 192.100, 0.63 over the MR of cyclohexane, which is 12 times by 6, 72, plus 12. That'll give you the number of moles on the left, and then do 1216 divided by 1,000 because I want it in. Wait, no, I do 1216 times by my answer, so the number of moles, and I get Q equals 9.12 over M, where M in this case mass of water, which is 50 grams of water, so 50 times by C, which is 4.18 given in the question. And then what I'm going to do is then first work that out, because delta T equals Q over MC, but Q needs to be measured in joules, right? So then I need to do 9.12 divided by 1,000 divided by 50 times by 4.18. Or do I leave it as that? Because I get Q 1216 times by the number of moles, which is the mass, which is 0.630 or 192.730 minus 192.100 divided by the MR, which is 72 plus 12. I get 9.12 as Q, using Q because delta H times by moles. Yeah, so then I get Q equals 9.1. All right. What I did was, I was like, okay, we need to convert into joules. Yeah, kilojoules to joules. I need times by 1,000, not divided by 1,000, because that's measuring kilojoules, because delta H is measuring kilojoules, given the question. So then I want to convert into joules. It's going to be 9,120 joules. Divided by 50 times by 4.18. That would give you delta T 43.636 recurring. But that's not what I want. I want the final temperature, so I'm going to do the initial temperature, 19.1, plus the answer I just worked out, 62.7. 62.7 degrees Celsius. And remember, because delta H Q divided by moles, Q is measured in kilojoules then, but I want it in joules. So kilojoules to joules, I times by 1,000. And vice versa, joules to kilojoules divided by 1,000. The dataable value is that, minus 392. So soon conclude that temperature rise was smaller than it should have been. So that's a practical reason for this. Heat loss, incomplete combustion, evaporation, that's fine. Use data in table 2 to calculate enthalpy change for the reaction represented by this equation. Now this one is with combustion data. Like 9 times out of 10 it gives you formation data, right? In this case it is combustion data. So combustion data, reactants minus products, whereas formation is always products. As per formation, products minus reactants, but in this case, it's the opposite way around. So products, reactants minus products. So it's going to be 6 times by minus 394 plus 6 times by minus 286 minus entropy of products C6H12. I'm going to have C3, 4, 5, 6. I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 CH bonds. Oh no, it's already giving me C6H12 minus 3920. 6 times by minus 394 plus 6 times by minus 286 minus 4080 minus 3920. Two negatives become positive. Answer plus minus 3920. Oh no, sorry, plus 3920 minus 160. Because it was multiple. I think the trickiest part is not falling for the trap immediately products minus reactants, because read the question. It says combustion data, therefore it is reactants minus products. Reactants minus product combustion, formation, products minus reactants. Give an equation for the complete combustion of octane. So C8H18 plus O2 and complete combustion, so I know my product's going to be purely carbon dioxide and water, H2O. 8 carbons left hand side, 8 here. 18, I need a 9 here. How many oxygens? 16 plus 9, that's 25. So I need 12.5 here. The combustion of petrol car and car engines produce pollutant nitrogen monoxide. Given the equation for reaction of removes nitrogen monoxide catalytic converter. 2CO, 2NO plus 2CO to N2 plus 2CO2. 2NO plus 2CO to N2 plus 2CO2. Question 4.3. Calculate mass kilograms of calcium oxide need to react with this mass of sulfur dioxide, and it tells me the mass of sulfur dioxide is that. I want to find the mass of calcium oxide. I need to react with this mass of sulfur dioxide. So first things first, moles equals the mass of sulfur dioxide. 1 ton equals 1000 kg, but I've got 6.49 million tons, so I'm gonna have. I've got 649. I've got this much tons, right? And I want to convert it to kg, so I'm going to add an extra 3 zeros at the end. But then I want it in grams. No, I want the mass in kilograms, sorry. So that's fine then, yeah. No, but mass, moles in mass over ml, mass is always measured in grams. So then you times it by 1000 again. So add another 3 zeros. Divided by the ml of sulfur dioxide, 32.1 plus 16 plus 16. Put on a calculator. 6490123 123 123 32.1 plus 16 plus 16. 1.012 times by 10 to the power 11. I want to find the mass of calcium oxide. I need to react to that moles and mass of ml. It's got 1 to 1 molar ratio. Mass is the moles, just worked out, times by the ml of calcium oxide, which is 56.1. And that would give me the mass. So I get 5.68, sorry, times by 10 to the power 12 grams. Because I worked out the moles of mass of ml and masses in grams, right? I want it in kilograms, and I divide by 1000, so it becomes 5.68 times by 10 to the power 9 kilograms. Draw a diagram to show how two methanol molecules interact with each other through hydrogen bonding in the liquid phase. So CH3OH, oxygen partially negative, hydrogen partially positive. Now we've got another. It does say include all lone pair electrons. So then lone pair electrons here, lone pair electrons here. No, then I need, wait. So what I'm going to have is, let's get rid of all this. So I'm going to have CH3, let's see what's that. I'm going to have oxygen, hydrogen, oxygen partially negative, hydrogen partially positive, two lone pairs of electrons, and I'm going to have the same thing here. CH3, oxygen partially negative, hydrogen partially positive, two lone pairs of electrons again, and then there's an attraction here, lone pair of electrons to the hydrogen partially positive, and showing two methanol molecules through hydrogen bonding in liquid phase. There you go. You should include partial charges, and the lone pairs of electrons in the two methanol molecules. While this bond angle is smaller than 109.5 degrees, lone pairs have greater repulsion than bonding pairs. Lone pairs have greater repulsion than bonding pairs. Okay. And then next part of the question says, describe the use of catalyst changes in pressure and temperature equilibrium reaction rate cost. Now what I'll do is, what is this? Delta is negative, so forward reactions exothermic, and therefore if I want to form methanol, right? So if I increase the temperature, equilibrium is going to shift to the left hand side. So what I want is a low temperature. So then therefore equilibrium shifts to the exothermic direction, therefore got more equilibrium yield of methanol. So I want a low temperature. But the thing about low temperature is slow rate of reaction, therefore compromises the use of low temperature. Do I want a high pressure or a low pressure? I've got 3 moles here, 1 mole here. So if I increase the pressure, equilibrium will shift to the side with fewer moles of gas to oppose the increased pressure, aka decrease the pressure. So it will shift to the right hand side, methanol direction, so more equilibrium yield methanol. So I want a high pressure. Once you've spotted that out, and then the catalyst bit, you just talk about no effect on equilibrium yield, however faster rate of reaction, and all of that. So now I know I want a high pressure and lower temperature for the highest equilibrium yield. So stage 1, let's talk about catalyst. Use of a catalyst has no effect on equilibrium yield. That's a key fact. However, equilibrium yield use of a catalyst gives faster rate and use of a catalyst lowers costs. Stage 2, temperature. Well, I want a lower temperature. Lower temperature gives a higher equilibrium yield. Therefore, high temperature gives a faster rate. However, the higher the temperature, greater the cost. Stage 3, pressure. Well, I want high pressure gives a higher equilibrium. Higher pressure gives a higher equilibrium yield. Higher pressure gives a faster rate. However, the higher the pressure, greater the cost. So temperature part and the pressure part, you just use exothermic, count number of moles, and then you see what happens if you want a high pressure or low pressure. And then you say that, but you also need to talk about the costs and all of that, equipment, faster rate, and then the compromise, right? And the catalyst part, that's the part. Use of catalyst no effect equilibrium yield. However, use of catalyst gives faster rate and it lowers the cost. Use of catalyst. Question 6. Name and outline the mechanism for the formation of E in this reaction. Alhamdulillah. Electrophilic addition. I'm starting with propene, methane. I could go through this way. Let me just go through this other way. Methane, ethane, propane. CH3. I have double bond here. CH2. Then hydrogen partially positive, oxygen partially negative. S double bond O, OH, double bond to here, double bond to the hydrogen, and here, and then what you've got is this, and double bond's gone obviously, and I can see here I've got this bonded to this carbon, which is bonded, which is secondary carbocation, so it's going to be here then. So the hydrogen goes here, carbocation is here, oxygen will lone pair of electrons, negative charge, S double bond O, OH, bond to it, and then you form CH3, CH, OS double bond O, OH, CH3. So CH2, CH, OS double bond O, OH, CH3. Perfect. Electrophilic addition. CH3, CH, CH2. Double bond to the hydrogen, middle of the OH bond. Oxygen is lone pair electron, negative charge, bonds to middle carbocation, bonds to lone pair electron, oxygen bonds to positive charge here, and then you form that. Draw the structure of F. Well, it says F is reacts with concentrated from two isomers. Well, this is the major product. F is going to be the minor product. So F, all that's going to happen is this OS double bond OH is just going to be bonded here. So it's going to swap around. So it's going to be CH3, CH2, CH, OS double bond OH. CH3, CH2, CH3, CH2, CH2, OS, double bond OH. And then classic question, I was like predicting this would come up, because why would it tell me to first go through mechanism, then draw the minor product, and then explain why more of isomer E's than F? Because isomer formed via more stable carbocation formed from secondary carbocation, whereas F is formed from primary carbocation. Positive, so E is formed from via more stable carbocation. 2I carbocation. Yeah, is formed from primary carbocation and secondary carbocation. Carbocation is more stable than primary carbocation. George Skeeter formula propane dioic acid. I think there's a question like this a couple of past papers ago, maybe last one before that. And the George Skeeter formula of ethane dioic acid. So you can see how it's just the same, right? You're just adding an extra carbon as propane instead of ethane. So this is why I need to go through these past paper questions. So propane dioic acid, methane, ethane, propane. No, sorry. So I'm gonna have methane, ethane. I'm gonna have OH. Okay, I'm gonna have a double bond O here, obviously. This is gonna be my HO here. And then again, I'm gonna have a double bond O here. And then instead of OH, and then the OH here. Perfect. This guy had to make this much an aqueous standard solution of propane dioic acid can accurately measure mass of the acid include essential practical details. In your answer, so number one, weigh out the sample in a container, add into volumetric flask, wash all sample in container, reweigh container, dissolve sample in deionized / distilled water, make up to mark / 250 centimeters cubed in volumetric flask, shake / invert to give a homogeneous solution is mixed evenly. Weigh out sample, weigh out the sample in container, add it to volumetric flask, wash with some container, reweigh container, dissolve sample with deionized / distilled water, make up to mark 250 centimeters cubed volumetric flask, shake / invert to give a homogeneous solution. Calculate the mass in milligrams of propane acid needed to prepare this much. So first thing I need to do is find out the moles by doing the concentration in moles per minus cubes divided by 1000 times by the volume. No, the volume times by the concentration. Then I'm going to use moles as mass over mR, therefore mass is going to be the moles times by the mR, which is 104.0 in the question. But that will give me the mass in grams. I want it in milligrams, so grams to milligrams. Then I'm going to times my answer by 1000. And that's imperative. So find out the moles first. 250 divided by 1000 times by 0.00500. Then times by 104.0. And then times my answer by 1000. And I get 13 milligrams. No, I don't. to find out the moles, done something wrong. 250 divided by 1000 times by 0.00500 times by 104.0 and times by 1000, 130. What I did was, I'm pretty sure I timed by 100, and that makes sense. That's why, no, not timed by 100, timed by, I don't know, but yeah, it's 130 once you time by 100. 1 time by 1000 to get it to milligrams. Question 8. Calculate minimum volume in centimeters cubed with this much due to oxide this much to propanol. I'm going to use density as mass over volume. Therefore, mass equals density 0.80 times by that's propane 10, volume of propane 10, 6.0. Then I can work out the moles of propane 10, which is just going to be 0.80 times by 6.0 divided by the mR, which they give us. So that's nice. And then I know I want to find out minimum volume in centimeters cubed of this much of dichlorate use oxide, this much of propanol. Now I find minimum volume of this. I've got 3 to 1 molar ratio. So I'm going to divide the moles that I get by 3. And then I've got the concentration of potassium dichromate 6 solution. I want the volume. Well then moles equals concentration times by volume. Therefore, I want to find out the volume. Volume is moles divided by concentration. Cross that bit out. So let's work out the moles. 0.80 times by 6.0 divided by 60.0, then divided by 3, and then do that, the number of moles divided by the concentration 0.40, and I get, but I want the minimum volume in centimeters cubed, so then times by 1000. 66.7 centimeters cubed. So density, mass, and volume, find out the mass. You find out the moles, and then you use 3 to 1 mole ratio and divide by 3, and then moles concentration, volume is moles divided by concentration. You got your moles, you got your concentration, but then that will give you your answer in moles per minus cube. You want the centimeters cubed, and then times your final answer 5000. Reaction done in a pear-shaped flask. Complete diagram to show some of the process needs to prepare propanol from propane 1L in this way. Now, there's no visual diagram on the mark scheme, so I'm probably going to skip this question. But it's just, yeah. Oh, it's giving me that. I just want to complete the figure, just filling in that. And you'll only know this how well you know your practical skills and memorize diagrams. Next question, question 9. Okay, almost done. Given equation, a breakdown of one molecule of this 1,2-dichlorotetrafluoroethane and one molecule chlorine molecule and one of the species. So I've got C2. No, sorry. CF2Cl, 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 CF2Cl. I know I'm forming a chlorine free radical 1 that, and therefore the remaining is going to be CF2Cl, CF2 free radical. So CF2Cl, CF2Cl to CF2, CF2, the chlorine well, the chlorine would have gone from there, so it's going to be then instead CF2CF2Cl. So CF2Cl, CF2Cl to CF2CF2Cl dot plus Cl dot. Give two equations showing how chlorine radicals catalyze decomposition of ozone. Cl dot plus O3, ClO dot plus O2, ClO dot plus O3, and 2O2 plus Cl dot. And these two equations you just have to memorize off by heart. This is not really whereas this one it give you this and it wants you to show the breakdown. CF2Cl, CF2Cl to CF2CF2Cl dot plus Cl dot. And this one you just need to memorize them off by heart. Cl dot plus O3, ClO dot plus O2, ClO dot plus O3, Cl dot plus 2O2. And then question 9.3, final question, 6 marks, and it says, Alhamdulillah. It says butane can be used as a replacement for CFCs in refrigerators. During its use, butane is repeatedly converted from liquid to gas and then back to liquid. Liquid butane expands as it turns into a gas. Calculate volume in centimeters cubed with this butane gas. Okay, so I'm obviously going to use, Alhamdulillah, PV equals nRT. I'm trying to find volume. nRT divided by P, the number of moles of butane gas, 38.8 divided by 58.0 times by 8.31 times by 272 Kelvin divided by 101 kilopascals, but I need pascals, pressure measured in pascals. That will give me the volume in dm cubed. No, sorry, that will give me the volume. Volume is measured in the ideal gas equation meters cubed. I want it in centimeters cubed. Centimeters cubed to meters cubed, I times by 10 to the power minus 6. Therefore, meters cubed to centimeters cubed, I times by 10 to the power 6. So I times by that million. So let's find out the volume first. 38.8 divided by 58.0 times by 8.31 times by 272 Kelvin over 101,000 pascals. That will give me the volume in centimeters cubed. Then I times by, no, that will give me the volume in meters cubed. Then I'll times by a million to convert to centimeters cubed, and I get 14,971. Then if you have to calculate volume of this much of liquid butane, density is that. Now, liquid butane density is that. I'm going to find out the volume. So what I can do is I know moles. Oh wait. Well, I know density is mass divided by volume. So volume is mass divided by density, which is 38.8 divided by 0.60, and which is 64.7 centimeters cubed. And then it says, use your answers to calculate the factor by which butane expands the volume when it changes from a liquid to a gas. So 14971 divided by my current answer at 232 is the expansion factor. So 14971 64.7 centimeters cubed 232. Perfect. And that is the end of section A.